Hello guys. So, and PewDiePie again, obviously. Who else do you expect? But this time I'm actually gonna do a very cool video. This is about linear independence. And no, it's not related to feminists or something stupid. No. This is mathematics. Okay, this is for vector spaces, linear independence. Why is it, let's say we have a vector, and this is going to be equal to some constant a1 times a vector e1. Oh, sorry, this doesn't look great. And also let me use a different color. 1, a2. Oh, sorry. This is actually wrong. I just need to add a plus sign. a2, e2 hat plus a3, e3. Let's say this is three-dimensional, but it can carry on to en, en hat, or you can use capital letter, which is nicer. So why is it that we say a vector is only linearly independent when this condition is satisfied only in the boring case? Let me just remove this. The boring case that all the an equals 0. That means a1 equals 0, a2 equals 0, and a3 equals 0. It has to be satisfied for all of them. I mean all of them. It has to be a very obvious and boring case. But why does this have to be true in order for us to call a vector linearly independent? And the answer is actually very simple. It's very simple, actually. Let me draw. So this is e1 hat, e2 hat, and this is e3 hat. Right? This is like my XYZ if you want, but not in this context. I'm using different symbols, not using XYZ. They can be pointing in any directions, but they have to point in specific directions. So I'm gonna explain. Don't worry. Now, let's say this can be 0 in the case that a1 is not 0, so e1 hat plus 0 plus 0. But that's a problem. Oh, sorry. Let me say this instead. I'm gonna change it slightly. e2 hat plus 0. So a3 equals 0, but a1 and a2 are not equal to 0. Now, can x, the vector, be 0 for this case, for this condition? Let me redraw that, sorry. Now I'm going to explain. It's obviously possible, but if that's the case, then x, the vector x, is not linearly independent. Let's presume that it's the case. Equals 0, right? a3, where a3 is 0, a1 is not 0, and a2 is not 0. Is that possible? But look at what you're saying. Look at what you're actually saying by doing that. You're saying we can express A1 E1 hat as minus A2 E2 hat. You know, put this on to this side. Put it on the other side so that you get this. Do you know what you're saying? I don't think you know what you're saying. You are literally saying that we can express. Let me make it more explicit. I'm going to make it so obvious what you're saying. You are saying that we can literally have this E1 hat equals minus A2 divided by A1 E2 hat. Now this I don't like. Hang on a second. 1 second. Let me change color. Let me go to this one. Let's call this another constant. It's a constant, right? Let's call it K. Okay? So E1 hat equals K E2 hat. You know what you're saying? I don't think you realize what you're saying. You are saying that E1 vector is a multiple of E2. If it is it's just a scaled, they are the same. They are the same. The same. Oh God, I'm so sorry. They are the same vectors, but with different lengths. So let's go back. Do you remember this graph I drew? Where is it? This. Do you remember this? This is the wrong picture. According to you, which is very wrong. If this can be true, that means we have E1, let me draw that again, and E2, which equals K E1 and E3. Now my question is, how many dimensions? How many dimensions? Only 2. Look, we only have 2 directions to represent. You don't have a 3-dimensional vector space. Do you know what that means? You know what that means, huh? I'll tell you what it means. It means we have an unnecessary, I don't know how to spell unnecessary. I think this is right. Unnecessary vector. E1 equals KE2, right? So we don't need E2. It's a redundant vector. I mean, why do you? It's like we have A1 E1 plus A2 E2 plus A3 E3, and then we do this. We say plus C E3 plus 2A B E3. But we can just add A3 E3 plus CE3 plus plus 2ab. Oh, just call it one thing. Like, I don't know. Okay, whatever. E3 equals constant. That's it. I'm done.